So rectangular pipe, yeah, it's along the z-axis from minus infinity to plus infinity. Let's draw how that looks like. So this is going, let's say that this is the z, x, y. Yeah, usually it's x, no, did I flip them? X, y, z. Yeah, x, y, z. Right? And this guy is going like this. So from minus infinity to plus infinity, yeah. This is the block. Okay, and has three grounded metal sides, y equals 0. So that's, so this guy is at v equals 0, y equals a, so this guy is at v equals 0, this being a here, yeah, and at x equals 0, so that this being here side, this is v equals 0. And the fourth side at x equals b, so this is b. The fourth side is maintained at some potential v0 as a function of y, so that means it's changing with the y, and it wants the potential, the general formula for the potential within the pipe, right? Okay, good. The best way to start this first, is this a two-dimensional problem or a three-dimensional problem?
This is two-dimensional.
Do you know why? It is two-dimensional, but do you know why?
Well, one dimension is constant. The z dimension doesn't vary.
Right. Do you know why it doesn't vary along the z dimension?
Yeah, because it's for when x equals a certain value, well, x is a certain value, then when x is b, then the potential is v of y. And
right, exactly. The potential as you move from one side to the other in the block is depending on the y value, because v0, I mean they're both, three sides are 0 and only one is at v0y, which means when you change y up and down, the potential changes, but along the z. Okay, so good start. So the first thing to realize is that this is a two-dimensional problem. So this is 2D, right? So now Laplace's equation, which is Laplacian, is this is equal 0. You know, there's no charge. Inside, we're solving Laplace's equation where there's no charge. So this will be, what's the Laplacian of v? This will become d squared v over dx squared plus d squared v over dy squared has to equal 0. So this is the Laplace's equation that we're going to try to solve. Yeah? This is the Laplace's equation that we're going to try to solve. So you know how to begin separation of variables. We're going to do this using separation of variables. And I'll give you a hint. So the first step is you assume, yeah, solutions of the form to separate the variables v xy has to equal some function of x times some function of y. So that's the first step to these problems. Yeah, some function of x times some function of y. I just called the big X and big Y.
It only.
Let's write the boundary conditions first to see how this is gonna. No, it's not gonna turn out. You'll see, it's gonna turn out to be sines and cosines and exponentials. It won't be 1 over. Because remember, this is the second derivative.
The second derivative.
Yeah. So look, let's write the first condition so we can see how the solutions will look like when we get them. So yeah. So boundary conditions. Okay. So what do we have for boundaries? We have 0, v equals 0 at y equal 0 and a. So v equals 0 when y equals 0. Right. And v equals 0 when y equals a. And v equals 0 when x equals 0. And at b, when x is b, this is where we have v0 function of y. Okay, so these are what the boundary conditions. Okay, so how do you go from here to the answer? Well, you say, okay, I'm gonna take now partial derivatives of this, and you plug them into the differential equation. So you know go back to this Laplacian, this solution. What's d squared v over dx squared? Well, y is independent, big Y is independent of big X, so this is d squared big X over dx squared times y, and d squared v over dy squared is just d squared big Y over dy squared. And now you plug those back into Laplace. Yeah? You understand what I'm saying? You plug those back into Laplace.
Yeah, wait.
Questions? You need to see the pad?
So, what do we do with the boundary conditions?
Oh, the boundary conditions, we'll wait till we get the.
So this isn't related to boundary conditions yet.
Yeah, it'll be soon when we plug them here. So you will get d squared x over dx squared times y plus d squared big Y over dy squared. So I'm plugging in the original Laplacian. And that's equals 0. Okay, now I need times x. Oh, I forgot the x here. Times x. Now I need to separate the variables. It's called separation of variables. So I need to separate the variables x and y. So divide this by xy. Yeah? Divide xy. So what do you get? If you divide xy here, the y cancels out, and you get 1 over x d squared x over dx squared plus 1 over y, right? Here the x cancels out, d squared y over dy squared, and that's equals 0. Alrighty? So far, so good. And now here, if you have two functions, the first is a function of x alone, and this one here is a function of y alone, and their second derivatives well, this function of x alone, this is function of y alone, and when you add them you get 0, and the only way this can happen is if those are constants.
Right.
The only way this can happen is if those are constants. So I'm gonna call this some constant k squared. This some constant, well, those are dependent constants, you know, because this is the constraint. But the question is, now I have to look at the boundary condition to get some information on what. So let's say I take the first equation, yeah. Let's say I take the first equation, right? What do I call this? Do I call it a positive constant or a negative constant? Is it plus k squared or minus k squared? Well, here you make an informative decision according to what the boundary conditions are, right? Because you know what kind of solutions you will get out of this. See, if you pick the k squared plus k squared and you try to solve this, you're gonna get exponentials. And if you pick the minus k squared and try to solve this, you're gonna get sines and cosines. So the question is, what does the x term accommodate? Sines or cosines? Sines and cosines or exponentials? Well, now you look at the boundary condition and you see that you need it to be 0 when x is 0.
Yeah.
And you need it to be some function of y when x is b.
Right. Yeah.
Right?
So
While the y accommodates
everything
0
Oh,
at
yeah.
0 and 0 at a. Well,
Right.
you can't make the y exponentials,
Right.
because you can't make e to the minus x and ex go to 0 at 0 and a, yeah,
Right.
because it blows up. While you could make the x be 0 at some value by just canceling out the term, and you can definitely make the exponential go to some constant value v0 and y. So the fact that y is zeros at both boundaries while x isn't, y has to be the sines and cosines, because you could make those easily disappear at the boundary, and the x term has to be the exponential.
Right.
So, so the x term has to be, so this term has to be the exponential.
Does it have to be the sine and cosine? Because it goes to 0 at x equals 0. And
so does the y.
But the exponential would go to e, or would go to 1 at x equals 0.
But you could fit zeros with sines and cosines. How could you fit the 1? The v0y, you see?
Well,
right, so
it could just be a product.
So you have to choose here.
Well, how can you fit a 0
with an exponential?
Because he says it has to be 0 at.
Yeah, you'll see. So we're gonna call this k squared, the positive one. Okay, and so this becomes g squared x over dx squared minus k squared x equals 0. Characteristic equation, or auxiliary equation, whatever you like. This is from your differential equation class. So I'll skip the in-betweens where you let y equal, or big X equals e to the mx. You differentiate, you plug them in, right? Remember? So you get straight to the.
Kind of remember that.
Here, I could show you.
Yeah.
I could show you if you want. The way to solve this differential equation is you say let big X equals right. It's a second order, so you need 2. So you need a. You let x be equals e to the mx. Okay, you know that the solution will have to be exponential. Okay, and then so you take the derivative of this with respect to x, so you get m e to the mx. You take the second derivative, right? So what's the second derivative of this? M squared e to the mx, and then take these and plug them here. So you get m squared e to the mx minus k squared. Yeah. Minus k squared. X is just e to the mx equals 0. Factor out e to the mx, so you get e to the mx into m squared minus k squared equals 0. This cannot be 0, of course, the exponential cannot be 0, so m squared minus k squared has to equal 0, so that means m has to equal plus or minus k. Okay, now since m could be k or minus k, you plug it back here, yeah? Right. So that means x has to equal e to the kx or e to the minus kx. Right. And you have a so if those are two independent solutions, which they are, you can test them. You can find the Wronskian, remember? If it's on 0. Yeah, if the Wronskian is on 0, they're linearly independent solutions. And if they're independent solutions, there's a theorem in differential equations that says if one is a solution, the other is an independent solution of it, then the sum is a solution. So that means a times the first plus b times the second is some other solution. So if this they're linearly independent. Yeah, if they're linearly. So this guy here is the x solution for the first one. Yeah. You wanna attempt the y now? So now we're done with the x. So this is how you solve it for the so you wanna solve it for the y? Yeah, exactly what you said is correct, yeah? So if one of them is x squared, the other one has to be minus x squared.
Right.
K squared. So that means this guy here, the y term, has to add to minus k squared. Yeah? Or no? Okay, so 1 over y d squared y over d minus k squared, and with the same exact logic you did before, you can derive. You'll find out that it's sines and cosines. Right?
That's where it starts.
No, you start with the y equation. We're done with v. We're down to the y.
I mean, I have v of y. That's what I use for big y's. So I don't confuse it.
Why you're calling it v? It gets kind of confusing because the
I call it v of y.
Because the assumed solution is some function of x. So you just called the y v of y, yeah. But you're gonna confuse it with the boundary condition. Okay, as long as it doesn't confuse you, it's fine. Yeah. It's fine, yeah. So, well, having said that, auxiliary equation, you could do the same thing I did. Assume solutions of
so that means that
e to the rx.
1 over y, d squared y plus k squared equals 0. Is that where?
There's no particular because there's no homogeneous part to it, yes. If there was a homogeneous part, non-homogeneous part, there isn't a function on the right hand side. Yeah. If there is, then you'd have to do this, then go back and take care of the non-homogeneous. Right. But this has no non-homogeneous, so it's all homogeneous. So yeah, it'll turn out like that. There's only the complementary solution. Yes. So yeah, so if I skip all these in between steps, I will get directly to the complementary. or auxiliary equation, whatever. Which I could have went directly to it here from the first step, because it's the second derivative that just gets you the m squared, and the other one is k squared x that just gets you x squared, and this has to add up to 0. So yeah, some people skip this and go down to here, and
to there, right?
Or directly to here if you know that this is minus, because this one is different now. This one will get you complex. Yeah, because when you do your auxiliary, you will get m squared equals minus k squared.
Right.
And you will get m equals plus minus ik. And if you use Euler, you will get sines and cosines. So y will turn out to be a sine ky plus b cosine ky. Skipping some steps to go from the exponentials to the sines and cosines, because you know they're off by a phase. So
I don't remember ever going from that. I just remember in every class I took, we would just go directly, like if there's an I that just meant we go to sine and cosine.
Right.
I don't remember.
Right.
I didn't remember actually like analytically.
Well, he didn't show you how to do it, but that's how,
I don't remember ever doing.
That's how you do it from scratch.
Well, I mean, I know that, but like when there's...
That's how you do it from scratch. And you might ask, how do I know that x is e to the mx? Because the exponential is the only one that repeats its derivative.
Right. I get
so
that, yeah.
So if you repeat the derivative,
right,
and you divide it by itself, this is the only way where you can possibly get some constant squared.
Right.
Yeah. Yeah, some of them probably don't know that.
But they somehow have a PhD.
They just, some of them just you'd be surprised how some people can get PhDs. How some people get their PhDs.
I've seen some pretty sad stuff.
People who, if someone has a PhD, that doesn't mean that they understand the material.
Yeah.
Or understand parts of the material in full.
Yeah. Actually, one time I even asked the teacher
Right, these exponentials, you could turn them with Euler's equations into sines and cosines, so you get a sine, b cosine.
Right.
Or the other way around, doesn't matter.
I can't believe that they never mentioned that in differential equations.
Yeah, that's the disadvantage of like doing these shortcuts in differential equations that I don't really recommend, because someone wouldn't be able to understand where things came from.
This is a complementary, and this is a complementary if there's I.
Right, and they never stress the because technically, technically you're getting e to the ik or ik plus e to the minus ik. And you're just turning this into sines and cosines by manipulating this, because these are ways. These are ways.
Yeah, and if you do I think that's basically because the derivative of that is the derivative of those things kind of switches. It follows the same pattern as the derivative of sine and cosine.
Right. Right. Exactly. Yeah. Okay. So having done that, now we can look at the boundary conditions. And see what the boundary conditions tell you about these equations and how we could fit them in. Yeah. We have 4 boundary conditions in total. 1, 2, 3, and 4. And so the first couple boundary conditions, they say, number 1, v has to be 0. So now remember what v is. V is the product of these two, x and y. Yeah, this is x function of x. So now my v is just I should use something different than a and b, because we're not supposed to be the same. So let's do C and D. So C, D. So now my V is AE to the kx. Oh, and by the way, you might wonder why I called them x squared, k squared, not k. Well, the reason is so I don't get into square roots, because I know I'm going to have to take the square root when I solve the differential equation, so I don't have a square root kx. I just call it k squared and, move on. So when I get to the step, I have a k. Okay, so a e to the kx, b e to the minus kx. Yeah, it's important to understand like why you're doing every single step you're doing. To make sense of this stuff.
Where it comes from.
Yeah, that's what I was saying about reading through the equations and being able to interpret them, and as you go and like you could forget the steps, but you won't forget like if you understand something you understood.
You can rederive something.
Yeah, exactly. If you forget. So this is d cosine. Yeah? And now you look at the boundary conditions. Okay. And what's the boundary saying? Well, boundary number 1 is saying that v equals 0 when y equals 0. Well, the only way that can happen, because when you plug in 0, cosine 0 is 1. This guy will survive. We don't want it to survive because it has to be 0. So d has to equal 0. Sine 0, 0, because if d is 0, the cosine term goes away and the entire thing is 0. So this guy is gone. Yeah? And boundary condition number 2 is saying that v equals 0 when y equals a. Y equals a. Was it a or b? Y equals a, yeah. So if that's the case, then the exponentials won't be 0, so that means the sine term has to be 0. C sine ky has to be 0. So either c is 0, and if c is 0, we just don't have I mean, this is a trivial solution if c is 0. Sometimes we do need to examine if c is equal 0, but not in this case. So that means the sine term has to be 0. That means sine ky has to equal 0. And what angles have a sine of 0? Those are the multiples of pi. So ky equals n pi. And this is supposed to be a, because now this is happening at a. And so that tells me immediately what k is. K is n pi over a. So if k is n pi over a, the sine term goes to 0 and the entire potential is 0. So this is a consequence of boundary condition number 2. Okay, sounds good. So now we'll go to boundary condition number 3. So boundary condition 1 said d is 0. Boundary condition number 2 gave us k. We still have to go to a and b. Now boundary condition number 3 says that v equals 0 at x equals 0. So let's deal with that. So 3, v equals 0 when x equals 0. Okay, well, let's see what that gives. So let's plug in 0 in what we have left. So we have 0 for the potential equals. If x is 0, we have a e to the 0 is 1, so that's a, plus b times c sine ky. Well, we said if this is, so either this can be 0, we've already examined this here, so we need to take the other one now. So a plus b equals 0, which makes a equal minus b. And by the way, I don't need the c constant anymore because I can absorb the c into a and the b. So I could just remove the c. And now that I found a relationship between a and b, so technically all I'm left with is one coefficient. Because a depends on b.
How do we get to the e to the
Oh, how to get from here to here?
No, how to get e to the I. More
This?
yeah.
Oh, because you get m squared equals minus k squared. If you take the square root of a negative number, you get an I.
Right.
Because k squared is positive and you have a minus sign here.
Right. And oh yeah.
The top one was k squared. It gave you exponentials. This one is minus k squared, yeah?
Right.
Okay, so now that we've absorbed everything in one constant, so this reduced our constants to 1. So now v, and I'll call that a. So v is equal to a, or c, whatever. Let's use c. E to the kx. And the other coefficient is minus c, so I'll factor out the c and just make this a minus. E to the minus kx times sine ky. So c e to the minus x minus c e to the minus kx, because one is negative the other, and I absorbed the sine coefficient into the c coefficient. We could do that. So now we're down to this guy here. Right? Now, of course, since k is n pi over a, I can remove it. But n could be anything. N is 1, 2, 3, 4, etc. And so technically, this turns out into a summation, right? Because the if 1 is a solution, and for n1, and n2 is a solution, and n3 is a solution, and n could be 0, by the way, too, etc., then their sum is also a solution, and all of a sudden my potential is basically a series from n equals 0 to infinity. Cn, each one has its own coefficient, e to the kx minus e to the minus kx times sine n pi over ay. And now we have to go and hunt that coefficient that we have created there, well, infinite set of coefficients, and for that I will consider boundary condition number 4. The last boundary conditions will enable me to get those coefficients buried in that series using Fourier trick. So what's the last boundary condition saying? The last boundary condition is saying that v equal v0y as some constant function of y when y, what was it, when y equals when x equals b, when x equals b. So I'm gonna plug it in, so I get v0y equals summation cn e to the k, which is n pi over a, b, minus e to the minus nb sine n pi over a y. Okay, and now comes Fourier trick, where I multiply both sides of this with sine m pi over a y here and here, right? And I integrate both sides with respect to y, dy yeah, from 0 to a. 0 to a. And why is that helpful? Because oh, by the way, this now became a double summation here, so mn equals 0 to infinity. Well, and that's helpful because if you remember, this is a Fourier series. These are constants. I could pull them out. Yeah. Well, wait, this is kb minus kb. These are 0 except when m and n are the same. That's what the Fourier trick is.
Okay. So where's
right? So when you integrate, except the places where they are the same,
they will all cancel out.
yeah, it'll all cancel out. So you see? So, and what's the value of this when you integrate Fourier, if you remember? This here is when you integrate that, you get either 0 if they're not equal. So this guy will either be 0 if n does not equal to m, and if n equals to m, you will get a over 2. You will get a over 2 if n equals m. So all the n's and m's will go away, and this series will turn out into just one term. Yeah, and so I'm gonna get from this Cn e to the kb minus e to the minus kb, and this guy here with the integral will become times a over 2. Yeah, times a over 2, and on the left hand side I could just integrate. Yeah, well, v0y, do we know what v0y is? Did he tell us? It's some function of y. Yeah, it's some function of y, which I don't think, yeah, it's general. So this will have to remain because we don't know what v0y is. This is just some function of y. Unless we know what that is, we can't really integrate it. Sine m pi over a y dy. So now I can hunt for my Cn. So Cn will be 2 over e to the kb minus e to the minus kb times this integral here, times 0 to a v0y sine m pi over a y dy. And if I take this Cn, so this is my coefficient, right? I can just plug it in here for v0, and that would be my potential. Yeah. Now in part B, he does tell you. He tell you, okay, well, so now we're sort of done, because you know this Cn coupled with this equation, right, characterizes the potential in the rectangular plate, right? So you just replace this Cn here with what we got. Now in part B, then he's more specific. He says, okay, assume that v0y is just some constant v0. So if that's the case, now you can integrate. So now Cn becomes, you can pull the v0 out of the integral, so this becomes 2v0 over e to the kb minus e to the minus kb. Oh, and by the way, k here I just didn't replace it, it's n pi over a, so maybe I should, because this is the final answer. N pi over a b, and this was n minus n pi over ab. Yeah, so and then you can integrate sine m pi over a y dy from 0 to a. Okay, so what's the integral of sine? So these here stay the same. Yeah, what's the integral of sine? We have cosine minus cosine m pi over a y, and then we multiply by the chain rule, which is we divide by m pi over a, or multiply by a over m pi, and this is from 0 to a. And now we can plug in, so we get minus a over m pi, and then whatever these are here, and then let's evaluate. So if you plug in the a, you're gonna get cosine m pi minus cosine 0. This guy is 1, and this guy will depend whether m is odd or even, right? So we will get minus a over m pi times these things. Yeah, now if so times, so if m is even, you will get 1 minus 1, you will get 0. So 0 if n is even, and if n is odd, you will get minus 1 if n is odd. Sorry, minus 2, because minus 1 minus 1. Okay, so we only get a potential if m is odd, so that means Cn has to equal, let me multiply these, so I get 2a over m pi, and I'm using m, so let me make this m, so m pi, so this is m here. Yeah, and then what's this, 2v0, so this becomes a 4 v0 1 over e to the kb minus e to the minus kb. You could change this if you want to cosine. I think this is cosine hyperbolic times 2, and then so this is your Cn, where m is 1, 3, 5, etc. So now the potential turns out to be, then if that's the case, just plug this back into our potential formula here. Yeah, so summation, yeah, so let me pull everything that doesn't have an m outside, pi, yeah, times e to the minus kb minus e to the minus kb, right? Then inside the summation, from m equals 0 to m equals the odd ones, 1, 3, 5, etc. 1 over m, yeah, so this is all Cm, and then we have e to the kx minus e to the minus kx. So e to the k is n pi over a x minus e to the minus n pi over ax times sine, I'm using m, let me stick to m, so m sine, what was it, sine m pi, yeah, m pi over ay, sine m pi over ay. So yeah, this is the potential inside the rectangular plate. This is the final answer, and we found exactly what, given that v0y is a constant, v0, this is what the potential inside looks like. You could change these if you want to cosine hyperbolic. I think, let me remember the,
Just the sine and cosine, but without the I.
Cosine hyperbolic is the plus, so this is the sine hyperbolic times 2. So if you want, this becomes right, yeah, this becomes sine hyperbolic. This here is also sine hyperbolic times 2. So if you want to rewrite this differently, you could say this is 4 over 2. This is 2, so you get 2AV0, right, over pi cosine hyperbolic, sine hyperbolic e to the sine hyperbolic kb, right? And then inside here you get m equal 1, 3, 5, etc. to infinity 1 over m, and this is also a 2 over 2, so this goes back to 4, yeah, because this is 2, yeah, so this goes back to 4, and you get here cosine sine hyperbolic m pi over ax, yeah, times sine m pi over ay. This is our potential. Either one works. Questions, Ben? Okay, there is an A in this final answer, which makes me a little suspicious. 1 second. There was an A when we integrated the average 2 over A. Where was it? Here it is, A over 2. So when we solved for n, we're supposed to multiply by 2 over A. Here it is. So this A here, I forgot to put the A here. So there's an A here. So this is 2 over A, which carries over. So then we have this A here, which comes all the way down, down. Okay, here we go. So we have an A here, and we have this A here, which crosses out. Okay, now it's making more sense. So let's put it in green, same color. So there's an A here that cancels out, and this A goes away. This is V0, the initial constant potential. Okay, here we go. Now the K, we can replace it by m pi over A, but see, this K depends on the m, so it needs to be included under the summation. So let me rewrite this term here. So this is sine hyperbolic K turned out to be m pi over A. It had an m, that's why we had to write it here, not outside, because it's depending on the summation as m goes over all the odd numbers b. So sine hyperbolic m pi over a b. Okay, so we can extend this. Okay, here we go. Now I think we are all set. Let's erase it from here. So here there's nothing but a pi. Okay, here we go. This is our final potential in that rectangular plate, and now the answer makes more sense as it doesn't depend on A, except of course inside the summation, but there's no A outside. Okay, sounds good. So this is our final answer here. Let's box it. That does it for this question. This was the separation of variables using 2D, x and y, independent of z.